Welcome to Chapter 5. We're going to look at some other examples that apply to those free body diagrams. We're going to introduce a little friction and talk a little bit about elasticity, about the way springs and elastic stretch and compress. So let's start out with friction. Friction, as we said in the previous chapter, acts to resist the motion. It will be along the surface that the object is moving on. So it's always parallel to the surface, and it always points in the opposite direction from the motion. So friction opposes the motion. It depends on the nature of the two surfaces. So if you have wood versus metal, or a rough surface on a smooth surface, that sort of thing. These will all make a difference. I know we all know this just from driving. If you drive on a dry road and then a wet one with a little rain, and then I hope you never have to do this, but an icy one, you can tell a real difference between those three surfaces. So it depends on not how big are the surfaces, but what kind of surfaces you have. We'll take just one little minute to talk about race cars and tires. I always like to mention that. My husband's a big NASCAR fan, and some of you, I'm sure, have seen the tires on a racing car. The ones that they run on these big races are actually, don't have any tread on them. It's a flat surface, and the whole idea is that the tire heats up as they drive along, and so it melts the rubber on the tire, and that helps to stick the tire to the road. So the whole point is to melt your tires a little bit so that they grip better and allow you to take those turns a little faster. We'll come back to this when we talk about cars going around turns. Now, we don't want bald tires for ourselves because we don't go fast enough to melt the tires, or at least I hope you never have to. All right, back to the topic. So there are two kinds of friction. We have kinetic and static friction. Kinetic friction is the friction between two moving surfaces. The formula for kinetic friction would be an F with a sub K. You can use a capital F if you would like to. I'm in a habit of using a lowercase f, but it really does not matter. So a capital F with a little sub K, and it's equal to, this is the Greek letter mu. It's a lowercase letter, and it looks like a U with a long front tail on it. So it looks like a U, but the leading edge of it has a long tail on it. So it is mu sub K times F sub N. F sub K is the force of friction measured in newtons. U sub K is the coefficient of kinetic friction. It does not have units of measurement. It's a proportionality constant. And F sub N is the normal force, which is also in newtons. All right, so we have kinetic friction when the surfaces, you've got movement. You have static friction if the surfaces are at rest. So if you park on a hill, you better hope you've got some static friction between the tires and the road. In fact, that's why when you park on a hill, they tell you to cut your tires in case your car begins to roll. It'll roll into the curbing, not let your car roll away. All right, so F sub K is for kinetic friction. F sub S is for static friction. And so the force of static friction is less than or equal to mu sub S multiplied by F sub N. So F sub S is the force of static friction in newtons. Mu sub S is the coefficient of static friction. Remember, it does not have units. And F sub N is the normal force, and it would, of course, be in newtons. I didn't apparently type that in, but by now we should know. Static friction is always going to vary. That's why there's an inequality sign here. It'll go from 0 to some maximum value. Static friction is always going to be greater than kinetic friction, and this is because of inertia. You have to overcome inertia in order to get things moving. If you want to think about trying to push maybe a car, to get it started on level ground might take a little effort. You have to overcome the inertia, so the static friction is larger. But once you get it rolling, it's not all that difficult to do. So static friction is always greater than kinetic friction. There's a table in your book for the coefficients of friction. You've got things like rubber on dry asphalt at 0.9 or on wet asphalt at 0.25. You can see there's almost a 75% reduction in the coefficient of friction as you go from dry to wet, which is why you should slow down on a wet highway. And certainly if you're going to try to change directions, like taking a curve. So let's do an example. We have a boy and he pulls a 10-kilogram box at a 30-degree angle with a force of 40 newtons. If the coefficient of kinetic friction is 0.1, then what is the acceleration of the box? So the mass equals 10 kilograms. Theta is 30 degrees. The force of the boy is 40 newtons. Mu sub k is the coefficient of kinetic friction. Mu sub k is the coefficient of kinetic friction, and it's 0.1. Acceleration in the y direction is 0. How do I know that? Because the box doesn't levitate and the box doesn't sink. No floating over the surface and flying away, no digging down into the ground. And we're going to make up and to the right positive because I'm going to make the boy pull the box to the right. And he's pulling it, not pushing it. So up. We want to find the acceleration. It'll be in the x direction, a sub x. We have our delta x equation, our acceleration equation, our average velocity equation. We have F equals ma and W equals mg, and the new one. Force of kinetic friction is equal to mu sub k times F sub n. Okay, you need some kind of a picture. And so what I have drawn in, here's our free body diagram. This is the box. The arrow pointing straight down is the weight. The arrow pointing straight up is the normal force. The diagonal solid arrow is the force of the boy, and he's pulling up and to the right. This little angle right here in the corner is the 30-degree angle. So he's pulling up and to the right. Friction pulls to the left. The two dashed arrows that you see represent the force of the boy in the y direction and the force of the boy in the x direction. So I took our force of the boy at a 30-degree angle and turned it into the hypotenuse of a right triangle. So again, the left-hand corner angle is 30 degrees. The hypotenuse is the force of the boy. The horizontal leg of the triangle is the force of the boy in the x direction. The vertical leg is the force of the boy in the y direction. We use this picture to come up with our horizontal and vertical force equations. And remember that friction always opposes the motion. So if the box is going to the right, friction goes to the left. All right. So horizontal forces, F total in the x direction equals m times a sub x equals every vector pointing right or left. We have the frictional force and we have the force of the boy in the x direction. And so they're just added together, the frictional force and the force of the boy in the x direction. For the vertical force, F total in the y direction equals m times a sub y equals 0. Why does it equal 0? Because we've said the box doesn't levitate and the box doesn't sink. Acceleration in the y direction is 0, so the total force in the y direction is 0. And now every vertical arrow, so that will be the weight, the normal force, and the y component of the boy's force. Those three forces will add up to give 0, our total force in the y direction. Just like before, when you have an angle, the first thing we want to do is resolve into components. So the first thing we want to do, step 1, is to resolve the force of the buoy into components. So I sketched the drawing. Looks like my arrow is a wee tiny bit too long. That's probably better. The force of the buoy is a diagonal arrow. This 30 degrees is this angle down here in the corner. Force of the buoy in the x direction is the horizontal dashed arrow. Force of the buoy in the y direction is the vertical dashed arrow. So sine is opposite over hypotenuse. So the sine of 30 degrees is the force of the buoy in the y direction, because if our angle is down here in the corner, the side opposite is right here, the y value. The force of the buoy in the y direction, and then divided by the hypotenuse, which is 40 newtons. To get the 40 newtons out of the denominator, you cross multiply. So 40 newtons multiplied by 30, the sine of 30 degrees, gives you the force of the buoy in the y direction, and that would be 20 newtons, and it points up because he is pulling, not pushing. If he were pushing, the arrows would have gone down. For cosine, cosine is adjacent over hypotenuse. So the cosine of 30 degrees is the force of the buoy in the x direction, because that's the adjacent side. Our angle is down here in the lower left corner. The adjacent side is the x component of the buoy's force. So force of the buoy in the x direction divided by 40 newtons. Cross multiply. So 40 newtons multiplied by the cosine of 30 degrees equals the force of the buoy in the x direction. And that turns out to be 34.6 newtons to the right. Now what? As always, we look at our horizontal and our vertical force equations and see if we can use them. We know the x and y component of the buoy's force. We know the mass. We don't know the acceleration, and we don't know F sub k. Down here, we know 0, the force of the buoy in the y direction. We don't know the normal force, and we don't know the weight. So it looks like we're going to have to calculate the weight. So to find the weight, weight is equal to mass times gravity. W equals mg, so 10 kilograms multiplied by 9.8 meters per second squared equals 98 newtons. And it points down. If you go back and look at your free body diagram, the weight points down. Now, we can use the vertical force equation. We know 0, we know the force of the buoy in the y direction, we just found the weight, we can solve for the normal force. But you say, wait, they didn't ask for the normal force. No, they didn't, but it is the only thing we can calculate, so we will. 0 is equal to 20 newtons minus 98 newtons. Why minus 98? Well, the weight is 98, but it points down, so it's a negative number if we made up the positive direction. And then plus F sub n. So 20 minus 98 is negative 78. To get rid of the negative 78, you have to add it to both sides. So the normal force is 78 newtons. It is a positive number. It points up. We still can't use the horizontal force equation because we don't know the force of friction, but we can find the force of friction. So we can find it using our new equation. F sub k is equal to mu sub k multiplied by F sub n. Mu sub k was 0.1. F sub n is 78 newtons. We just found that. So 78 times 0.1 is 7.8. It's measured in newtons, and it goes left. How do I know that? I look at the free body diagram. I look at the free body diagram. Now we can find the acceleration. We can use that horizontal force equation. So F total x equals m times a sub x equals the force of the boy in the x direction plus the frictional force. So the mass is 10 kilograms. A sub x we do not know. I'm sorry about the little squiggly underline. I thought I had fixed all those, but apparently not. Force of the boy in the x direction was 34.6 newtons, and it goes right, so it's a positive number. Force of friction goes left, so it's minus 7.8 newtons. So 24.6 minus 7.8 gives you 26.8. Divide both sides by 10, and you get 2.68 meters per second squared. How do I know that a newton divided by a kilogram is a meter per second squared? Because we're finding acceleration. And acceleration is measured in meters per second squared. So here are some problems you should try for homework, and there are also problems on the study guide in the assignment. Let's talk a little bit about drag forces. We're not going to do anything with them. I wish we had time, but we do not. Excuse me. There's a section in your book on drag forces, so if you're interested, you should read more about it. You see these when you have your object passing through some sort of a fluid like gas or a liquid. Drag forces actually play a really big role in the design of race cars and in the design, surprisingly enough, of the swimsuits that you use in the Olympics or speed skating suits or things of that nature. These are all designed to reduce the drag. Drag is dependent on the shape of the object and the kind of fluid you're in, how fast you want to go, and other factors. So if you can reduce the friction that the fluid experiences as it moves over a surface, you can reduce drag. There are a lot of things in nature that have streamlined shapes to reduce drag. Fish and geese in flight and all kinds of things like that. So it's really a very interesting topic. I just wish we had more time to spend on it. All right, moving along. Elasticity, stress, and strain. So when you compress or stretch an object, you have to apply a force, and the deformation is going to be proportional to that applied force. So we have an equation called Hooke's law that is associated with things like springs or bungee cords or things of that nature. Hooke's law is F equals minus K times delta L. So the F is the force measured in newtons. The K is the spring constant measured in newtons per meter. And capital L is the deformation. Please remember that delta L is change in length. So that'll be final length minus initial length. Final minus initial length. And if you think you're not going to remember it, write it down. Delta L equals final length minus initial length. So what that means is delta L can be positive if you are stretching something and negative if you're compressing it. And sometimes we leave the minus sign out. It's all about, in physics, they wanted the force associated with compressing a spring to be a positive number. And the only way you can do that is if K is negative in this equation. All right, enough of that. So springs and rubber bands and bungee cords, and in your body, your tendons all have a spring constant. So if we look at the graph, we've got force on the horizontal axis and delta L on the vertical axis. There is a limited range for any springy material where it will obey Hooke's law. And then you get really closely, and then you get to an area where it obeys it, sort of, kind of, maybe. And that region is called, so we've got the elastic region where it has elastic properties. And then if you keep stretching it, what's going to happen is you'll have permanent deformation. You may have seen this if you had a rubber band wrapped around something for a long time and then you take it off and you notice your rubber band doesn't snap back like it used to. And then finally, if you stretch even more, you can obviously break a rubber band. So springy things have a fracture limit. Let's look at our example. What's the spring constant for a spring that starts out 0.4 meters long and is compressed to 0.35 meters by a force of 12 newtons? So we know that L sub 0, the initial length, is 0.4 meters. We know that the final length, L sub f, is 0.35 meters. We know the force is 12 newtons. We want to find K. So F is equal to minus K multiplied by delta L. We'll write our formula down. F equals minus K times delta L. So the force is 12 newtons. We have minus K written down. Delta L would be L final minus L initial. So final length was 0.35, initial was 0.4. If you take 0.35 and subtract 0.4 from it, you get negative 0.05 meters multiplied by negative K will give us our 12 newtons. To undo multiplication, you divide, so we have to divide both sides by negative 0.05 meters. We have to divide. So if we divide both sides by negative 0.05 meters, 12 divided by that gives you negative 240 newtons per meter. That gives you the negative of K, so K would be positive 240 newtons per meter. 240 newtons per meter. And that stops the chapter. It was short. So be sure to do your homework.